Okay, it's a pleasure to have Professor Peter Stone in our seminar today. Dr. Stone is the holder of David Bruton Jr. Centennial Chair at UT Austin Computer Science Department. He received his Ph.D. from the Carnegie Mellon University, and his research interests include reinforcement learning, multi-agent systems, and robotics. Professor Stone is a Sloan Research Fellow, Guggenheim Fellow, AAAI Fellow, IEEE Fellow, AAAS Fellow, and ACM Fellow. He's also a Fulbright Scholar and an ONR Young Investigator. He is also a recipient of the HGI Computers and Thought Award and the ACM SIGAI Autonomous Agents Research Award. Professor Stone serves as Executive Director of Sony AI America and is a co-founder of the startup company Cogitai. Cogitai, sorry. I was privileged to have him on my own PhD dissertation. And with that being said, I leave the stage to Professor Stone.
Great. Thank you very much for the kind introduction, Mohammed, and thanks everybody for being here. I deeply apologize for the late start in 2 years of Zoom. I've never had this happen before, that my laptop wasn't able to connect. We tried, I'm improvising here a little bit, and I guess what I should first do is ask you for a little bit of guidance. Should I cut the talk short and make it about 45 minutes long, or should I do the whole thing and you know, people can just leave if they need to at the top of the hour? Which do you prefer?
I personally can stay, but I mean, I think you can just go with your normal one, and yeah, people who want to leave, they can leave earlier. One more note, if you had any questions, please post on the chat box, and I'll ask them on your behalf.
Great. So it's a pleasure to be here, and you know, I wish I were there in person. In fact, I have very fond associations with ISI. I think the first invited talk I ever gave as a graduate student was at ISI. That would have been back in 1994, I think, the summer. I was invited to talk about our paper, a JR article called Flex, a flexible planning system that I had worked on, and so I've been there several times. I have close colleagues with many people there, and so very honored, and thank you all for inviting me and for being there. So the talk I'm going to give today is actually, it's a complicated talk. I'm going to talk about lots of different things, and that's part of the reason it's, if it had been working perfectly from my laptop, I'd be jumping smoothly between a bunch of different slide decks. Because we're scrambling here, I'm going to have to sort of pull some decks up as we go, so bear with me. But I'm going to start by just giving a quick introduction to what's going on here at UT Austin. I'm at UT Austin right now. Let's see if I can move this thing out of the, oops, I didn't mean to be drawing, I mean to be moving this. How do I, okay, there we go. And is my screen share? Yeah, wait, is my screen share still there?
No.
Yes?
No.
No. Oh, okay. What happened? I was just trying to move the little dialog box out of the way, and it seems like, oh, there we go. Okay, I can share the screen again. Okay, I'll leave it alone. I'm here at UT Austin, and we've got some exciting things going on. We were awarded one of the first NSF AI institutes, the Institute for Foundations of Machine Learning, and formed a machine learning laboratory around that. I'm a founding member of an AI cross departmental interdisciplinary organization here at UT Austin called Good Systems. which was a sort of a grand challenge project that now involves social scientists and humanists and technologists, very much aligned with the theme of this talk on autonomous agents for social good. And I'm also the director of Texas Robotics, where we have a beautiful new facility. We'll be hosting ICRA 2025 here. There's lots of faculty now who are publishing in the core robotics conferences here at UT Austin. So I do a bunch of different things in my lab, and I'm going to give you a sampling of them today. But the thing that unifies them is this question: to what degree can autonomous intelligent agents learn in the presence of teammates and/or adversaries in real-time dynamic domains? I publish in many different research areas within sub areas of artificial intelligence, as shown here. And when I give sort of a one-slide introduction to my lab, I usually do it in the context of the application domains that interest me. And so I'm not sure if these videos will work on this. No, they won't. So I've been motivated very much by the robot soccer domain. I'm right now the president of the International RoboCup Federation, where our goal is by the year 2050 to have a team of humanoid robots that can beat the best World Cup soccer team on a real soccer field. A part of RoboCup is also trying to create general purpose service robots like the ones shown here that can interact with people in natural environments. I've also been very motivated by autonomous driving applications. And very recently, one of the things I've been most excited about in my role as executive director of Sony AI, we just published a paper on the cover of Nature on outracing champion Gran Turismo drivers with deep reinforcement learning. And so I'm not gonna give the talk here, but Sony AI does focus. Our mission is on unleashing human imagination and creativity with AI. And we recently, as I said, published a paper that appeared on the cover of Nature that just sort of takes its place in this series of successes of AI beating the best human experts at complicated domains. It's happened in chess and checkers and poker and Go and Jeopardy and so on. And this is in a very real driving simulator called Gran Turismo. And just to give you a sense of it, I can show you what it looks like. So.
There's very few places where you can go out and say, I'm going to build an AI and I'm going to make it truly superhuman.
We're going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Gran Turismo Sophy is a super exciting project. It's an amazing AI research and development activity.
There are many racing games where the physics is half done, but in Gran Turismo, that racing sensation that the players get, that's really at the core of the game.
このなんか車文化、車という存在をもう丸ごとビデオゲームの中にこう再現したいなと思ったんですね。
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophy agent?
This is not just a technical breakthrough project. It really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースしていきたいなっていうふうに思いましたね。
So I could give you a full talk on Gran Turismo Sophy. It's a really fun project, but that's not the plan today. There's a lot of information on the website. One of the benefits of working for a company that makes movies is they can make flashy trailers like that. But really, there was we had to devise a new reinforcement learning algorithm. There's some really interesting multi-agent systems issues that came into that. But what I'm going to do today is talk about various projects in my lab around that sort of coalesce around the theme of learning and multi-agent systems for social good. I'll start with a project on learning agents, in particular about reward design for reinforcement learning. I'll then talk about a pure multi-agent system setting that's on traffic flow optimization. And then sort of at the intersection, learning in multi-agent systems, I'll talk about a simulator we developed for improving pandemic response by government agencies. So to jump in, I'll start with the reward design. And like I said, I'm gonna have to jump around a little bit here. So apologies that I don't have this already pulled up, but there we go. Okay, so this is a paper that we recently published. It was the first author is shown here was Brad Knox, a former PhD student of mine, along with several other collaborators. And it's on sanity checks for reward design and cost. This is really familiar to anybody who's worked in reinforcement learning, is the alignment problem. How do you make sure that the reward signal that your system is trying to optimize is aligned with what you want your agent to be able to do? You know, because the optimization of a reinforcement learning agent is limited by the metric that it's being optimized against. And this was sort of an interesting study of the literature to show that reward design, specifically as it's been used for autonomous driving, has been very problematic in a way that I'll sort of drive home in this presentation. So first of all, just a background on reward. Again, if those of you who know reinforcement learning, there's usually this concept of G is the notation, tau is for a return, for like a sum of rewards over time. Tau is a trajectory, so that's the parameter of a return. So you get a return for a trajectory, and it's the sum of the rewards you get for all the time steps along the way. And so, you know, the question is, how do you define your reward function that's sort of that comes one step at a time for a state action and next state, such that you get the proper ordering of trajectories, the one that you want. And this is a ubiquitous concept, not just in reinforcement learning, but in motion planning, control theory, evolutionary algorithms, utility theory. There's sometimes different words used, but it's all really about the same thing. There's a return and there's a reward, and there's some kind of relationship between those. If you look in the literature on reinforcement learning, there's very differing and often very complicated reward functions that people design. So here's just a sampling of 4 different papers, and they, as you can see, they sort of weight either that's the sum of 4 different attributes, that things like your change in speed or the proportion of the vehicle overlapping with the sidewalk. There's parameters to tune, like a +100, -50, -10. These are sort of manually engineered, and the way you engineer them really affects what the system will end up learning. It is the only signal it gets to learn. And so in this study, we looked at 19 papers, and it's focused in on especially 10 that defined reward functions for autonomous driving, and identified some of the sort of problematic features of those. And first of all, there's a lot of reward shaping that goes into them. And what that means is in addition to the true thing you care about, the true environmental reward, people put in sort of hints, behavioral hints or heuristics, like that last one I showed, try not to overlap with the sidewalk. That might not actually be your reward function. That might just be, a person observes that the reinforcement learning agent is going over the sidewalk sometimes, so they add another reward signal to keep you away from the sidewalk. And this is sort of against the textbook way of doing reinforcement learning. Reinforcement learning, that everybody says the goal of setting up an RL problem is to specify how to measure the outcomes, not to give hints on how to achieve them. So in general, don't try to shape rewards. But the problem is that when you have a sparse reward signal, when an agent only gets to find out at the very end of a chess game whether it won or lost, that can be very difficult to as a signal to learn from. And so it's very tempting and often necessary to give some kind of some kind of shaping reward or some kind of hints. But the problem is, in almost all the cases that people do this, they do it in a way that changes the actual ordering of the trajectories. So basically what we would say is unsafe reward shaping. And there are ways known in the literature to be able to do safe reward shaping, but in general, we found that almost everybody is doing some form of reward shaping, and in many cases in a way that actually isn't guaranteed to keep the ordering over trajectories the same as the true reward function. And so this is just a tendency, and often people don't even recognize that they're doing shaping. And so they don't describe the separation between the shaping rewards and the true rewards. They don't recognize that this is an issue, and this is something that is I think really important for the community when it comes to alignment. The other thing we observe is that that again, we wanted to reason about trajectories, and so you want to make sure that your reward function would order a particular trajectory. If everybody agrees that one trajectory is better than another one, then the return of that trajectory, the sum of the rewards, should be greater than the return for the other trajectory. So let's consider two particular trajectories. One in which a driver, it's successful, but for half its trip, but then crashes on the way to the destination, versus a trajectory that the car never leaves home. So which of those two would you prefer? Almost everybody would say, I'd prefer, if I knew I was going to get into an accident on this trip, I shouldn't have left home. So this idle trajectory should be better than the crash trajectory. And yet in seven of the 9 papers, the reward function they defined would prefer this crash trajectory over the idle trajectory. That seems problematic. Even more so, and this is, I think, the most sort of the most salient take home from this study that from my perspective, is that if we look at sort of comparing indifference points, so we had the idle trajectory, which we already agreed, or I already asserted, was better than the crash trajectory. You can imagine another trajectory that successfully gets to the destination that's better than the idle trajectory. So I think everybody would agree that there's this total ordering over trajectories. And then you can say, well, what's my indifference point? With what probability would should there be a trade-off between crashing and getting to my destination, such that I'd prefer to take the trip rather than idling? And so we can, that's sort of a measure of risk tolerance. And in the papers that we looked at, I already said 7 of the 9 papers that we looked at carefully have defined a reward function where crashing was preferred over idling, which is not right. The 2 that did otherwise, their indifference point was orders of magnitude more risky than even a drunk US teenager, statistically, right? So people are defining reward functions that are just inherently not reflective of what we would think of as the trajectories that we would want for their autonomous vehicles, and we see this as being quite problematic. And so in the paper we put forward a bunch of different tools for evaluating reward and cost functions to try to help people identify whether they're doing things like these examples that I just characterized, and some of them here. I already went through comparing indifference points and preference orderings and unsafe reward shaping, and there's several other sort of guidelines that we provide in this paper. Of course, this is this isn't a comprehensive evaluation. We looked at a limited number of papers. We looked at a single domain, autonomous driving, but I think it's very instructive for the importance of reward alignment if you're doing machine learning for social good, meaning you care about the outcome, not just whether the agent can learn or not, but that you care about the trajectories that it learns are in the right kind of ordering that you care about. So that's the sort of the first little vignette I wanted to provide. Moving on to multi-agent systems, we've looked a lot at optimizing traffic flow as a multi-agent system, and this I think is something from a societal perspective, from a social good perspective, is critical. There's tons of time wasted. There's tons of emissions and fuel wasted. There's a lot of statistics you can look up on how sort of how egregious this is in our society, and how important it would be to be able to mitigate this. So I'm going to present some work that was done, led by a former postdoc of mine, Guni Sharon, who is now faculty at Texas A&M, on a particularly, I think, ingenious mechanism that he came up with for mitigating some traffic congestion in a way that does take into account sort of, you know, the social aspects of it. So this is in the context of modeling traffic networks. And first of all, it's important to recognize that there's lots of different ways of modeling traffic networks. There's sort of macro level modeling where you think of flows between points as being continuous. And then there's down at the micro level where you model individual cars. There's also meso level modeling that's sort of a cell transmission model where you have, you know, sort of somewhere in between those two. I'm actually going to talk about all three of those modeling levels. This was joint work with some civil engineers using tools that and terminology that they that they use, and it was especially a faculty colleague of mine, Steve Boyles, who was an important collaborator in this work. So starting with macro level modeling, the way you model traffic in a macro level is, like I said, with continuous flows. So you think of there being, you know, a starting destination V1, a starting point V1, a destination V2, maybe two roads in this simplified network, and then like some kind of a trip table which says, you know, what's the demand for the network. So let's assume that we have a trip table that just has all 100% of our cars want to go from V1 to V2. In general, you'd have a much more complicated one. And then you also have latency functions. So it could be that, you know, this link, no matter what the number of cars on that link, it's going to take 1 hour, whereas on this link, it's a function of how many cars take that link. So, you know, in particular, if you do this kind of model, then, and you let every car figure out where it should go on its own, they're all going to take the bottom link, because as soon as you move one car to the top link, it takes an hour to go, and all the other cars are taking a little bit less than an hour because there's, you know, not a full 100% of the cars. But there's a much better solution, which is that if we could get, you know, if we could induce 50% of the cars to take the longer link, then you know they would take an hour, but the other 50% would each take half an hour, and the average flow of the system would be 3/4 of an hour. And so, and this is, you know, this is, you know, commonly known as sort of the price of anarchy, or there's, you know, the difference between the user equilibrium, which is everybody optimizing for themselves, and the system optimum, which is a centralized controller telling all the cars where to go. Now, in general, you don't want the you know, such a centralized controller. You know, people, it would be very hard to, you know, to implement, right? People are all going to want to make their own decisions. If Waze tells them, I've got a route that goes through the city that'll take 59 minutes, or I can take another, you know, longer route, the scenic route that takes an hour. You know, the user might still say, even though it's going to cause more congestion in the city, it's going to be bad for for social welfare, I still want to do the best I can. I still want to take this 59-minute route. So how do we mitigate this? How do we go from anarchy to the system optimum? One way is providing incentives, and you know, how do we get them to act altruistically? And so, you know, tolling is one way to do this, and this is a common way. And it's not always a popular way, right? Polling, and so I'll get to that later in this portion of the talk. What do we do if we don't want to impose tolls? But let's assume for a moment that we can impose tolls on every road. Then there's a well-known concept of marginal cost tolling. It's very similar to if you know auction theory, it's like a Vickrey auction. It's that each player pays their social cost, which is basically how much everybody else does, how much slower everybody else goes compared to if that system were not in, if that driver were not in the system. So, you know, if there's this, you know, the turtle here causes these two rabbits to slow down by an amount of time that's equivalent to $1 in delay, then the turtle should pay $2 in tolls. And it's actually known in theory that when applying in this sort of macro model, if you apply marginal cost tolling, the user equilibrium and the system optimal align. But the problem, you know, can we do this in practice? How do we apply marginal cost tolling in practice in this macro model? this is where some input from our colleagues in civil engineering helped a lot. We can assume that there's some form of latency function, which says basically, what's the marginal impact of the 15th vehicle being added to the system? So like say we have 14 vehicles, here's the travel time. We added one more vehicle. It's going to increase the travel time shown for everybody, shown by this blue curve. So then we can basically say that the marginal cost toll for the X for a vehicle, adding a 15th vehicle is 15 times the slope of this curve, right? So in other words, the marginal cost toll should be the number of cars in the system without you times the slope of this latency function. So where do we come up with this latency function? It turns out there's a well-accepted one in the civil engineering community called the Bureau of Public Roads latency function. And it's defined as follows. And you don't have to understand the full algebra of it. You can go through this in the paper if you're interested, but it includes things like the time to traverse the link, currently with the current traffic conditions, and T sub 0, which would be the free flow travel time if you were the only car on the road, and then traffic volume, and then a few parameters, couple parameters, the link capacity. So this is that latency function, and so we can take the derivative and multiply by x. We get an expression for the marginal cost toll. So that would be all well and good, but the problem is there's some parameters here in link capacities that there's some things here that can be observed, the current travel time, the free flow travel time, the traffic volume, but there's these other things that are somewhat more problematic. How do we come up with them? It turns out it's not practical. There's not an easy way to sort of figure out how you can convert this to a toll. But Guni came up with a really nice sort of observation, which I'll show on the next slide. There's a lot of people who've looked at this before. Like, there are all kinds of tolling schemes that make certain assumptions as shown here. I'm not going to walk through them, but you can see them on the slide. It turns out that we can define a method called delta tolling that's particularly simple to implement. And this appeared in Transportation Research Part C, also in the AMOS conference, a preliminary version of it. And we take that BPR latency function before, and if you take and that I showed you before, this is the form I already showed you. It turns out with a little bit of algebra and replacing terms, it simplifies to a parameter beta times. You can basically substitute this, which is our latency function, into the derivative, and that so that amounts to t, which is the current travel time on our link, minus the free flow travel time. So the marginal cost toll really it simplifies to a simple expression of the free flow travel time and the current travel time on the link. And these are both observable, and it leaves us with just a single parameter, this parameter beta. And so it turns out this is actually easy to implement. We can put it on any road and just say every car is going to have to pay this toll. So if we can experiment with different latency, like actual latency functions, and then look in a bunch of different networks, and it turns out that delta tolling yields the provably optimal flow. Even though every car is going to just take the self-interested route, we get the social optimal route. Now that's in the macro setting, and I said that's a simplified model of the environment. It's unrealistic, particularly in that it simulates flows in a static setting instead of modeling individual vehicles. And so if you go down to the meso simulation or micro simulation, you can get more realistic and do what's called dynamic traffic assignment, or DTA. And the difference here is that each car can now change its route or change its demand based on the current traffic conditions. So like if there's congestion at one link, even if a car has started moving, it could say, oh, I'm going to reroute and take a different route. And you can also have sort of influences from the intersection, queue spillbacks. You can model lane changing and stop signs and things like that. And so this is where we now go to, from the theory where we got the provably optimal system optimum, we're trying to make it work in this dynamic traffic assignment scenario with micro simulation or meso simulation, and as is often the case, theory and practice don't perfectly align. There's new challenges when we try to implement. In particular, we get some oscillation effects that there's a time at which you measure the current traffic flow on a link. You use that to set a toll. The cars make decisions based on that toll. That changes the traffic conditions, and you could get big oscillations. Everybody goes one way, and then the tolls change, and everybody goes another way. And so, to mitigate this, we found that we needed to reluctantly add a second parameter, a parameter R, a smoothing parameter, where if it's set to 1, we're fully adaptive, but we're susceptible to those oscillations. If we go to 0, then we're back to the sort of static case where there's no the tolls get set once and get fixed there once and for all. And so, but now once we have this, we can actually evaluate in our 2 sort of meso simulation models, a cell transmission model where there's sort of discrete places that cars can be, and there's no turning modeled or anything like that. And also in microscopic traffic models where they actually model steering and braking and acceleration and detailed kinematics and things at the expense of much more computation, of course. And when we do this, we found actually that this delta tolling in this dynamic traffic assignment scenario with relatively constant, similar values for these 2 parameters, the smoothing parameter and the beta parameter, got significant reductions in total system travel time. That's the metric we use. So in other words, add up the travel time for all the cars to get from their source to their destination compared to if we didn't use tolling. And so again, these reductions are really actually dramatic in the traffic world. This could amount to huge amounts of savings in terms of time, fuel use, and emissions. And we did it across a range of scenarios. So, we were really excited about this. But does this solve the problem entirely? Well, as I've alluded to, we do have some parameters, these R and these beta parameters. And so, we may want, it would be nice to be able to tune those in real time. And so I'll talk about that briefly. To really roll this out, any kind of system, you have to make sure that there's no really worst case performance, right? You can't take some time to learn or get the system into equilibrium, but some days have traffic just get to complete gridlock. And so, then that'll make the national news that there was, 1 or 2 horrible days of traffic and, due to this autonomous system. So you'd like to be able to bound what's the worst case performance of using this kind of a system. And as I also alluded to before, that tolling is often not politically popular, and so can we get around that? And so just briefly, I'll talk about these 3 extensions. For tuning this beta and the R parameters, which is basically the proportionate. The beta is the proportionality constant. How much toll should you get for times this difference between the free flow and the current traffic conditions? It turns out you need them to be different for different conditions, we actually found that you would want ideally to have different parameters for each link in your road to really optimize the system. You might want one pair for highways, another for side streets, and so on. If we were going to do this by brute force, by hand tuning, that would be a non-starter. But it turns out that we could actually, if we use some black box optimization methods, using either gradient descent or evolutionary strategies like CMAES, that we can find parameters across a whole system. So we actually used, I think in the paper we ended up using CMAES, which is this derivative-free gradient-based optimization method that converges to a local optimum, not global optimum, but it's can deal with pretty high dimensional spaces. And by putting a separate R and beta parameter on each road and then optimizing in this way, we get a method that we call enhanced delta tolling that improves significantly beyond the delta tolling results that I showed you before. So on many of the same scenarios, getting even further reductions. We have another paper that I think I'm not going to go into in detail here, but you know, to try to mitigate these worst case performances, we analyzed theoretically that, you know, if we both mainly in the macroscopic model, that if we have an error factor, if you know, we already told you that in theory, if you get the true marginal cost tolls, that it leads to the system optimum, and you know that you can't, there's nothing to complain about there. But if you have some error in estimating what this the tolls should be, a question is, you know, would that lead us to massive instability and really bad travel times? And so, you know, we asked the question, what's the worst case that could happen if you have an error in your estimation of the delta tolls? And it turns out that if we underestimate, we can prove if we underestimate by a constant factor, traffic won't get worse. That under certain conditions, a local optimum is guaranteed to be a global optimum. And so I'm not going to go, in the interest of time, I'm not going to go into the full details of this theoretical analysis, but it's in our AMOS 2019 paper. And then finally, we looked at, you know, trying to get these same benefits without actually imposing tolls. So one way, you know, and the key observation is that to be able to get to the system optimal, you don't have to influence all the drivers, right? In the example I showed earlier, if you can divert 50% of the drivers, you can get to the system optimal. The others are already doing what's in their best interest, so you don't even have to toll them to you know, get them to do what you want them to do. And so we asked the question, well, how many, to get to the optimum, how many drivers do you need to influence, or you know, said another way, what percentage need to be compliant to the tolls? And we can answer that question using a linear program that's shown here on the right. We looked across a number of scenarios, and relatively surprising, you know, I think surprisingly, you only need to influence a relatively small number of cars in several cases to be able to get to the full system optimum. So one of the solutions that we've been that we've explored is this concept of opt-in tolls, where rather than putting a toll on every road and everyone has to pay it, you give people a choice. You could either pay tolls throughout the year, but if you do, you'll get sort of a prepayment ahead of time to do so. So, like, you know, your tolls will be, you know, if your expected toll value is going to be about $200 annually, what if I paid you $400 to opt in? And then you can decide every day, do you want to, you know, pay the toll, or do you want to take the, you know, the cheaper route? If you don't opt in, then just go ahead and take your, you know, the road you would rather take anyway. So in other words, it's a, you know, sort of voluntary toll, and you're expected not to come out behind, you know, if there's some subsidization here. So we looked at that and examined that paper, you know, that in a particular paper. And we've also been looking at, you know, you could also think of this as you know, just a pro-social influence. If Waze would tell you, you know, there's one route takes 30 minutes and one route takes 60 minutes, well, almost always you'll take route A, the one that takes less. But what if we told you, you know, and even if we told you that route A would take 30 minutes and route B would take 31 minutes, you'll still choose route A. But what if we told you, you know, route B will take 1 minute longer, but it'll also reduce overall emissions and fuel consumption. It'll help children get home from school faster and safer. And maybe even, you know, if you take this route, then, you know, then today we'll give you, you know, a faster route. You know, we'll encourage you to take route A tomorrow, or something like that. Right. So there's these sort of, you know, pro-social effects that can be explored as well. So this you know, body of work is summarized on this slide. That, you know, we've found a way to improve traffic flow, which I think is a really important aspect of autonomous agents and multi-agent system for social good. Providing some implementable, pretty you know, fairly easily implementable method called delta tolling. It's practical, a way to tune some of the parameters for it, and also, you know, that can come with some performance guarantees and even mechanisms for addressing this without imposing tolls as it's motivated by. Okay, I'm actually moving along. Okay, so let me just briefly show some related work that we've been doing on also traffic optimization. This is ongoing work in collaboration with General Motors. A former student of mine, Daniel Urieli, is a collaborator who's now at General Motors. It's on scalable multi-agent driving for reducing traffic congestion. Oh, and this video isn't playing in this version, but you may have seen there's some great work coming out of Berkeley, Alex Bain's lab, first author Eugene Vinitsky, on traffic networks, where even if you go in a circle, I'll sort of describe what this video would show. If you put a bunch of cars in a circle and tell them all to go the same speed, you still get sort of traffic waves. One of them goes a little bit faster or a little bit slower than you told them to, and so you get this sort of wave of congestion that goes around the circle. And they showed that in that sort of system, if you give a single car the ability to modulate its speed or learn what speed it should use using reinforcement learning, it can make the whole system go more smoothly. And so we've looked at expanding this, and basically, having if you just have a small number of autonomous vehicles in the road, and you have and you could control what speed they go at, can you use reinforcement learning and distributed reinforcement learning, so you have multiple of them, to optimize their speed so that you sort of get stop these waves from happening, both in not just in a circle, but in sort of open networks where there's merging in from different lanes, and much larger scale networks than have been considered before. And I think I'm not gonna talk further about this work. There is an AMOS paper in 2021 that I can point you to. But rather, what I'm going to do is, for the last segment of this talk, and is talk about the simulator we came up that we've deployed and released open source for pandemic response. And this is joint work with some folks at Sony AI, and also here at the University of Texas at Austin. In particular, Lauren Myers is a world-leading epidemiologist, and we couldn't have done this without her input, and also her colleague Spencer Fox, who were sort of guiding us on how to make this useful and realistic. One of Lauren and Spencer's, Lauren and Spencer, one of the people who created one of the models that is used by the sort of national aggregate model to track COVID, and still is, and they're very much in touch with the policymakers. And we have a Journal of Artificial Intelligence JR article describing the details of this. So the motivation here is to manage the impact of COVID-19, a very topical area for social good. You're all familiar with these graphs, I'm sure, at this point, where the goal is, if the yellow line is your hospital capacity, then you don't want the top graph where you exceed hospital capacity and don't have enough ventilators. You don't want the middle graph, which you never pass hospital capacity, but you have to really shut things down to achieve that, and keep everybody at home and close down the entire economy. What you really want is to sort of stay safely below your hospital capacity with some margin, but keep the economy open as much as possible, and relax restrictions as much as possible. And the methods that Lauren and her colleagues, the epidemiologists, were using were generally what we would call a macro model, akin to what I just showed you in traffic simulation, is continuous models, where you model a population as a single continuous number. The contribution here was to create an agent-based simulator that models the community interactions. And we're not the only people who have gone down this path, but I think we've done this hopefully in a way that's useful to others, and that is particularly grounded both in the agent-based community and in the epidemiology community. And the idea is that the spread of disease is modeled as an emergent property of people's behavior, models realistic effects of imperfect testing, variable spread rates among the infected, the potential for not following the regulations, not wearing masks when the government tells you to, contact tracing, etc. We've released an OpenAI Gym interface to enable support for reinforcement libraries. I'll talk about how that comes in. And we optimize and analyze a reopening policy learned through reinforcement learning. So The control loop of the simulator, as you can imagine, is that there's people that go through sort of a routine during the day. There's a government that sort of observes what's going on with its population and issues regulations, and that's where the seat of the learning is going to happen. So we're going to try to come up with a government policy that will keep the population going as smoothly as possible. At night, we have update rules that change who's infected, where they're going to go, who's in quarantine, and so forth. And so to see what this looks like, here's just a small run of the simulator where in real time you can see how many people. The green line is people who are not infected yet. The yellow line are people who are infected. You zoom in on that was zooming in on an office building during the day where people are moving around. The pink is people's homes. There's a grocery store. There's a hospital, and people sort of people are modeled by these dots, and they move around according to some behavior patterns. And when they come across somebody who's infected, they can also get infected with some probability. So some examples of location rules that we coded in. There's grocery stores, offices, schools, retail stores, hair salons. They have opening and closing hours. They can be locked or unlocked based on regulations. There's a hospital, and the government can modify these. And then there's also people behaving. So stochastic behaviors. There's a working person will go to their assigned office during the day. A child will go to their assigned school. People visit stores once per week and hair salons once per month. At night, people stay home, but every once in a while, there's social events that draw people from across the city. People go to hospitals unless the hospital is full, in which case they have to stay home. Some people flout the regulations. And then we have an infection model. Again, I'm sure, unless you've not been paying attention the last couple of years, you're very familiar with these kinds of models. This is basically an SEIR model, but with some extra fidelity to it, where people are modeled as either susceptible, exposed, pre-asymptomatic, pre-symptomatic, asymptomatic or symptomatic. So that's, they're in all of these cases, they're either infected or going to be infected. They can be critical, hospitalized or not. They can be recovered, they can die. And then there's probabilities that are governed by what we learned from the epidemiologists. So infection probabilities are calculated based on their actual contacts between people in the simulator over the course of each day. So you only can possibly get infected if you cross paths with somebody who is infected. And there's a spread rate sampled from a bounded Gaussian distribution. There's super spreaders that have higher rates, incubation periods, number of days that's probabilistic, but roughly 2.5 days before becoming infectious and testing positive. And then the actions that the government can take, and this is based on exactly the Austin city guidelines. In fact, today, as I speak to you, we're in stage 2, but only last month we were in stage 5 as Omicron was at its peak. And these do things like tell people how big a gathering should you have if you're high risk versus low risk, who should be in quarantine, these sorts of things. And so the actions that the government can take are just moving these stages. And then the reinforcement learning can come in to try to say, what government policies should you use? And we did experiments in sort of a small population, 1,000 people, 300 homes. So you see the sort of parameters here. And then we defined a reward function to try to, a relatively simple reward function. Just negative rewards if the hospital number of critical people was above the hospital capacity, and negative reward for being in higher stages. So basically encouraging being as open as you can or unrestricted as you can, but without affecting the death rate in hospitals. And we also did include on the topic of the first part of this talk, some shaping rewards. But in this case, only a single one, which was try not to change stage too often. Like we don't want to bounce back and forth between stage 1 and stage 4. We only use that in some of the experiments. And then we did training using reinforcement learning. We could collect data from the simulator. We used a off-policy actor-critic method called soft actor-critic, where we could gather data from the simulation, sample a batch from the data buffer, update the policy and critic parameters using a standard SAC methodology. And if we do this, we would get, sort of, we could then see, what happens compared to some baseline policy. So here's like a policy just always at stage 0. So in other words, no government restrictions. This shows how there's a huge peak over the hospital capacity, and our reward is very low. We're always at regulation stage 0 compared to an always be at regulation stage 4. And that sort of gets us the graph, where you never exceed hospital capacity, but your reward is low because you're very restricted. And then we could learn using SAC a more stochastic policy that depends on the current current population statistics, and we get this more sort of bouncing around a little bit, never exceeding hospital capacity, but and what it learned to do actually was to sort of gradually ramp down, go up very quickly to stage 4, and then gradually ramp down back to stage 0. And this was only with a single, the first wave of the pandemic that we were studying here, not new waves and new variants. And in the paper, we do a much more detailed analysis. And we also we calibrated the simulator by what happened in Sweden, where they had no restrictions because they stayed at stage 0 the whole time, versus Italy, which had the very quick movement to stage 4 and stayed there for a long time. We did some other hand-coded policies. Here's one that did ramp up to stage 4 and then gradually ramped it down to stage 0, as I sort of showed in the previous. But it turns out that if we learn, we can do better than even that. So here's that policy I just showed you. Its cumulative reward was in the negative 7.5 range. With 3 different learning runs, shown here. It bounced around a lot but then when we got a better cumulative reward if we put on that shaping, that restriction that you can't change the policy very frequently. Then there's fewer changes, but still better reward. And we also evaluated it. Well, here's one where you couldn't change the restrictions except once a week, every 7 days. So there was a little bit of a cost to it. We also evaluated on a population of 10,000 people, the same learned policy. So not learned on the population of 10,000, but learned on the population of 1,000 and applied in a population of 10,000, and also doing quite well. And just I'll wrap up because I know we're in the interest of time. I want to leave time for questions. But we also are looking at now what happens if there's vaccinations. That's getting modeled into the simulator. And we've done some preliminary experiments in that scenario as well. But really the summary here, and this is, I've mentioned, this is from when we were showing it at an actual conference, but the summary here is that we've learned an RL policy that optimizes a reopening strategy, balancing the infection and economic costs. It's actually now appeared in JER. And the main insight that we found is the best strategy is to switch gradually from complete lockdown to no restrictions, but to get to that high restrictions early on. And there's many possible next steps: conducting longer experiments with larger populations, adding more types of locations, higher fidelity model of schools, exploring structured stage policies, trying different learning algorithms, post-processing the network results for explainability, and continuing with vaccination models and running RL experiments. And the nice thing is this is an open source simulator. You can download the code, it's in Python. We very much welcome contributions, and we just learned yesterday actually that's about a colleague we didn't know about who was using it and just completed the study. And so we hope that it will be very useful for researchers now, and eventually that methodologies like this will help us be more prepared to advise governments when inevitably the next pandemic comes down the road. So with that, I've thrown a lot of information and in a relatively short time. I apologize for the slightly late start, but there's lots more details on any of this that you can find. The reward design for reinforcement learning paper, here's the archive link. The 2 traffic flow optimization papers you can find in a couple of venues as shown here, and this pandemic simulator you can find in Journal of AI Research. And that's that's sort of a, like I say, a sampling and a whirlwind tour of some of our work here in the Learning Agents Research Group at UT Austin and at Sony AI America on autonomous learning agents and multi-agent systems for social good. With that, I'll thank you again for your attention, for the invitation to come here, and be more than happy to stay around for a little bit to answer questions if there are any. But of course, I won't be insulted if anybody needs to leave because we're past the top of the hour.
Okay, thank you for your presentation. Any questions from the audience? Okay, I have a quick question. So for the last portion of your talk where you were using RL in your simulation, I noticed that the numbers that you were using are relatively small, and RL is known to be data greedy. Do you think that your simulation is scalable to like real world scenarios, like say something like New York City, which used to be epidemic at the beginning?
Yeah, so this is the reason that we did that experiment where we learned on a small population and evaluated on a larger population. Admittedly, it was from 1,000 to 10,000, not up to millions. The limiting factor here is not the reinforcement learning. I don't think it's the running the agent-based simulator, right? So it's the gathering the data to put into the replay buffer for the reinforcement learning. The larger the population, the more you have to model who's going to work, who's going to schools, what kind of interactions did they have during the day, who's infectious, all of that. And so, being able to scale up the simulator, and I think there have been, this is not where we focused our energy. I think the research in the community on digital twins is very focused on trying to get larger and larger agent-based simulators of cities. And so, I think if there's potential to partner and to work with people who do that. I think, like I say, that as long as we can get the data from the agent-based model, the agent-based simulator, the reinforcement learning will be up to the job.
Okay, thanks. Okay, I guess there's no more questions. Thank you again for your presentation. And I guess we'll shortly have your one-to-one meetings.
Great. Thank you very much. And thanks everybody again for being here. It was a pleasure.
Thank you all.